This excerpt introduces the plasma state and sets the roadmap for the chapter. It separates nonequilibrium, man-made plasmas into glow discharges, corona discharges, dielectric barrier discharges, DBD, and microwave plasmas, and it links each to industrial applications. It then transitions to thermal, man-made plasmas, and explains the basic concepts used to generate them. Where useful, the text points forward to later chapters for deeper detail on specific plasma sources and use cases. At the particle level, molecules, atoms, and ions exist in fundamental states or excited states. Because excited species have short lifetimes, energy is often released quickly as photons, which contributes to plasma luminosity. The excerpt also notes Bremsstrahlung, where an electron is deflected by an atomic nucleus and emits electromagnetic radiation while losing kinetic energy. Figure 1 places the plasma state alongside solid, liquid, and vapor, showing how temperature and specific enthalpy, mJ/kg, relate to phase and to the presence of ions and electrons. A key theme is that plasmas carry high energy content compared to solids, liquids, and ordinary gases, which is why they enable many applications. To anchor the field, the text points to classic references in plasma physics and engineering. It names Cobain in 1958, Brown in 1959, Campbell in 1963, Michener and Kruger in 1973, Parrott in 1992, Bittencourt in 2004, and Friedman in 2004 and 2008. These citations frame the discussion as part of a mature engineering discipline rather than a niche topic. Plasmas often have densities low enough to obey Maxwell, Boltzmann statistics rather than Fermi, Dirac, or Bose, Einstein statistics. Even so, their dynamics are more complex than ordinary gases and fluids. One reason is weak Coulomb scattering, which can make electron and ion mean free path comparable to or larger than macroscopic plasma length scales. Another reason is long-range electromagnetic coupling that allows collective modes, such as plasma waves, where many charged particles act in concert. The excerpt defines plasma temperatures in terms of the average kinetic energy of each constituent species. EQ 1 expresses the Maxwell-Boltzmann idea that temperature corresponds to average particle kinetic energy. For narration, the key meaning is that heavier species and electrons can each have their own effective temperatures depending on how energy is injected and redistributed. This sets up why non-equilibrium plasmas can have hot electrons while the bulk gas remains near room temperature. Collisions drive systems toward equilibrium, but the rate depends strongly on mass ratios. EQ 6 gives the average kinetic energy exchange in an elastic binary collision and shows that energy transfer is most effective when the two masses are comparable. As explained using Howatson in 1965 and Chang and Pfinder in 1990, electron-to-heavy particle energy exchange is inefficient because the electron mass is much smaller. That is why even with high collision frequency, there can be persistent differences between electron temperature T and heavy species temperature Th. The text then discusses local thermodynamic equilibrium, LTE, and partial local thermodynamic equilibrium, PLT. Beyond thermal balance, LTE requires excitation equilibrium and chemical equilibrium, and it also imposes limits on gradients in the plasma. For discharge plasmas, the excerpt emphasizes the reduced field measures, E/P and E/N, where E is electric field and P or N characterizes the neutral background. For narration, the point is that these ratios are practical knobs that correlate with electron mean energy and thus with reaction pathways. A simple but useful classification is natural plasmas versus man-made plasmas. Figure 3 illustrates one such classification by placing common sources on a spectrum of energy levels and ionization. The excerpt uses the Sun as the most accessible natural plasma example. Figure 4 connects the Sun's immense output to thermonuclear fusion in the core, where temperatures reach 10 to the power of 6 to 10 to the power of 7 K, and the plasma is essentially fully ionized. Solar magnetism drives phenomena that shape near-Earth space weather. The text notes that the interstellar medium near hot stars is dominated by ionized hydrogen created by ultraviolet radiation. It also highlights coronal plasmas, citing Ashwaubenon in 2004. Figure 5 shows aurora borealis as a large-scale, diffuse, low-luminosity event, while Figure 6 contrasts it with lightning as a massive electrostatic discharge in the atmosphere. The excerpt transitions from natural plasmas to man-made electrical discharges. It describes the discharge tube with parallel electrodes under a direct current, DC, voltage. Using the relation E equals V/D, it explains that the electric field inside the tube increases with applied voltage V and decreases with electrode spacing D. For narration, this relationship matters because it connects the hardware geometry directly to the conditions required for breakdown and sustained ionization. The text explains how free electrons accelerate toward the anode and trigger further ionization through collisions, forming an avalanche. It then introduces Paschen's law, EQ 13, which links glow discharge breakdown voltage to the product of gas pressure P and electrode gap D. The practical meaning is that there is an optimal P times D where breakdown occurs at the lowest voltage. The excerpt relates these regimes to Figure 8 and notes how the system transitions from glow to arc behavior as current increases, with arcs approaching LTE at higher currents. Glow discharges are introduced as a core non-equilibrium plasma source with broad industrial relevance. Figure 9 presents the physical structure of a non-equilibrium discharge, often in AR or other noble gases, and it contrasts hot electrons with a much cooler heavy particle temperature. The text notes that DC glow discharges require a conductive cathode, and that pressure, voltage, and current are interrelated. It also points out that pulsed operation in DC or RF modes can raise instantaneous power without overheating electrodes. Quantitatively, the excerpt gives typical electron number densities for the negative glow region in the range of 10 to the power of 15 to 10 to the power of 16 per cubic meter, with electron energies around 1 to 2 electron volts. It describes the positive column as having a small positive electric field on the order of 100 V/m. For applications, it cites solid analysis with glow discharge and points to Marcus and Brocard in 2003. It also links glow discharge conditions to plasma-assisted physical vapor deposition and chemical vapor deposition, where vacuum and mean free path control whether sputtered particles can reach the substrate. For coatings, the text explains magnetron sputtering as a way to intensify sputtering using a magnetic field behind the target. The essential meaning is that electrons follow longer spiral paths, increasing ionization and sustaining a denser discharge near the target. When reactive gases are added, nitrides can be deposited, and ARC-PVD is cited by Erkins and colleagues in 2011 for tools and components. Figure 11 provides an example with TNPVD-coated tools, connecting the discharge physics to visible industrial outcomes. Corona and streamer-like discharges are discussed with an emphasis on non-uniform fields near sharp electrodes. The excerpt warns that a key risk is transition to an arc and list control approaches, such as limiting voltage and using pulse power supplies. Figure 15 compares short and long exposure images for discharges in a 40 mm gap in atmospheric air with a 54 kV pulse and a 30 nanoseconds rise time, illustrating how transient structures emerge. For narration, the takeaway is that timing and waveform shape can be as important as amplitude for maintaining a desired discharge mode. Dielectric barrier discharges, DBD, are explained as self-limiting discharges that stop when space charge at the dielectric cancels the applied electric field. Because of that self-limiting behavior, DBD normally require alternating voltages, and the dielectric acts as a ballast. The excerpt states that DBD are typically operated from 50 to 60 Hz up to about 10 MHz, depending on configuration and current limitation. Figure 17 shows micro-discharges in a plate ozonizer, and Figure 18 shows discharge tubes in a technical ozone generator. linking geometry and gas flow to ozone production at industrial scale. The text then turns to microwave plasmas and other electromagnetic coupling methods. It explains that electrons oscillate with the electromagnetic field and transfer energy to heavy particles through collisions, while high-energy electrons maintain ionization. It lists applications such as abatement of fluorinated compound gases, including hydrofluorocarbons, perfluorocarbons, and SF6 from semiconductor fabrication systems. It also cites decontamination of chemical and biological warfare agents and plasma-assisted chemical vapor deposition, PACVD, as further industrial uses. Thermal, man-made plasmas are introduced as hot or equilibrium plasmas, with the caution that diagnostic methods like emission spectroscopy can be misleading if excitation equilibrium is not satisfied. The excerpt then describes thermal arcs and the need to generate enough charge carriers for the gas to become electrically conducting. For stability, it explains arc stabilization mechanisms and shows induced flow behavior in Figure 21. It also notes that at sufficiently high currents, for example at greater than 100A, macroscopic flow velocities can reach the order of 100 meters per second, which strongly affects heat transfer and arc behavior. Plasma torches are presented as practical thermal plasma sources where an arc is struck between a cathode and an anode nozzle. The narration-relevant meaning is that injected plasma gas is heated by the arc and exits as a high-temperature, high-velocity plasma jet. Transferred arcs are illustrated with Figure 23 and Figure 24, including a case with a 100 mm arc length and a 750 A arc current. The excerpt also introduces inductively coupled plasmas as electrodeless sources and later points to Figure 43 for a typical ICP-OES plasma source and Figure 44 for an ICP-based cladding setup used in fiber optic preform processing. Plasma spraying is used to explain how thermal plasmas deposit coatings across multiple industries, including aerospace and nuclear. The text describes splat formation as molten particles strike a substrate at 100 to 300 meters per second and build a coating layer by layer. Figure 33 and Figure 34 connect this process to large-scale components and jet engine hardware. It also notes cathode spot behavior, giving spot diameters of 1 to 2 millimeters for currents from 800 to 1,400 A and current densities of 10 to the power of 8 to 10 to the power of 9A/m², emphasizing why electrode erosion becomes a practical maintenance constraint. In metallurgical and waste-related applications, the excerpt frames thermal plasma as a tool for melting, remelting, and high-temperature chemical processing. Figure 37 shows a plasma shaft furnace used for scrap remelting and illustrates how power input, gas flow, and tapping streams integrate in a furnace system. It introduces waste-to-energy transformation and plasma vitrification that gasify organics, melt inorganics, eliminate voids, and bind hazardous metals into a ceramic matrix. Figure 39 presents an MSW destruction concept, connecting plasma torches to slag formation and off-gas handling requirements. High-power source concepts are illustrated with segmented and stabilized arc heater designs. Figure 40 presents a conceptual design of a segmented DC plasma torch with multiple electrodes, constrictor modules, and active cooling. Figure 41 shows a wall-stabilized, segmented high-power arc heater attributed to NASA, emphasizing that extreme power, pressure, and current require modular conduction paths and aggressive thermal management. For narration, these figures highlight that scaling plasma sources is less about a single component and more about coordinated electrical, thermal, and fluid design. The excerpt closes with examples of induction plasma processing for materials refinement. Figure 46 shows plasma deposition of refractory metal coatings on an X-ray target and on cylindrical substrates. Figure 47 compares electron micrographs of molybdenum powder before and after treatment in an AR/H2 induction plasma and points out improved sphericity and density. The practical meaning is that induction plasma can reshape particle morphology and improve packing behavior, which directly affects downstream manufacturing performance.